Thanks for tuning in to First Principles Daily, episode 30 for July 5th, 2026. Today's question, what would this cost if you only paid for the atoms? Replacing a lead service line costs thousands of dollars, yet the pipe material itself is worth only tens of dollars. The price is almost entirely in the digging, records, and restoration. Millions of homes still draw water through lead service lines that run from the street main to the building. Each replacement today routinely runs into the thousands of dollars per connection, even though the replacement pipe, whether copper tubing or cross-linked polyethylene, can be bought by the foot for a small fraction of that total. The gap between those two numbers points to an operations problem rather than a materials problem. It is the kind of gap first principles reasoning is built to attack. Because the atoms themselves are already inexpensive, any serious reduction in total cost must come from changing how crews locate, schedule, excavate, and restore each individual run, rather than from negotiating a lower price per pound of copper or polyethylene. Municipal water systems grew over many decades with little centralized mapping of the smallest service connections. Crews therefore begin each job by locating the line, often through trial excavation or ground-penetrating radar that must be scheduled and permitted separately. Ownership is split between the utility and the property owner, so two separate approvals and sometimes two separate contractors are required before work can start. Once the trench is opened, crews must work around gas lines, electric conduits, tree roots, and varying soil conditions that differ from one address to the next. After the new pipe is inserted, the same trench must be backfilled, compacted, and surfaced to meet local standards for asphalt, concrete, or landscaping, each of which carries its own inspection. Because every address presents a unique sequence of these steps, crews cannot standardize tooling or crew size the way a factory production line can. Regulatory requirements for lead abatement notification, water quality sampling before and after the swap, and traffic control add calendar days that keep equipment and labor tied to a single site. Fragmented procurement means each utility or contractor negotiates small lots of pipe, fittings, and restoration materials rather than buying at commodity scale. Carrying costs accumulate while a single replacement waits for permits, locates, and inspections that can stretch across weeks. The result is that the dominant share of reported project expense sits in mobilization, permitting, excavation, and surface restoration rather than in the pipe or fittings themselves. Safety rules and inspections apply to every site, so the question becomes whether they can be satisfied once per neighborhood instead of once per address. Soil and utility conflicts are genuinely different at each house, yet the time spent discovering those differences could be reduced if earlier records were digitized and shared rather than recreated on every visit. The current process therefore treats each connection as a standalone construction project whose fixed costs are paid in full every time, even when the variable material cost remains trivial. A rough magic wand estimate begins with the physical length of a typical service line, often between 30 and 60 feet. Copper tubing of the required diameter trades at commodity prices that place the metal value in the low tens of dollars for that length. PEX tubing, an alternative now accepted in many jurisdictions, carries an even lower material cost on the order of a few dollars for the same run. Add the handful of brass or plastic fittings, a shutoff valve, and perhaps a meter setter, and the total raw material value remains well below $100 in current commodity markets. Reported replacement projects, by contrast, commonly reach several $1,000s per connection once all field and administrative steps are included. Dividing those two figures produces an idiot index on the order of 50 to 100 or higher, depending on the exact city and the condition of the surrounding pavement. That ratio is not fixed by physics. It is produced by the sequence of locating, excavating, permitting, and restoring each individual connection. The largest single block of cost arises from opening and closing the street or sidewalk, because heavy equipment, traffic control, and pavement restoration must be mobilized and demobilized for every address. A second large increment comes from the absence of reliable records. Crews spend hours or days confirming the route and depth before they can cut. Permitting and notification cycles add further delay that keeps labor and equipment idle between jobs. Because each site is treated as a bespoke project, learning from one replacement does not automatically reduce the time required for the next. The gap therefore lives almost entirely in coordination overhead and per unit field labor rather than in any scarcity of copper, polyethylene, or brass. Commodity prices fluctuate, yet even if copper doubled in price, the material floor would still remain well under $200, while finished costs sit in the thousands. The ratio would shrink only modestly. Some cities already achieve lower totals through volume contracts, yet those savings still leave the idiot index far above the material floor because the underlying per-site coordination steps have not changed. The arithmetic therefore shows that the dominant opportunity is not in the atoms, but in the sequence of decisions and movements required to place those atoms in the ground. A redesign would begin by creating a single, machine-readable map of every service line, built from existing maintenance tickets, meter installation photographs, and municipal construction archives rather than from new excavation. Machine learning models trained on those historical records could predict the most probable route and depth for each remaining line, cutting the hours spent on physical locates. Once locations are known in advance, crews could shift from open trench excavation to keyhole or trenchless insertion methods that require only small access pits and avoid full pavement removal. Standardizing the connection hardware across an entire utility territory would let suppliers deliver pre-assembled kits at commodity volumes instead of custom orders. Policy changes that align public and private ownership under a single work order would eliminate duplicate permitting steps. The hardest constraints are the physical variability of soil, the presence of other utilities, and the need to maintain water service during the swap. Any new method must still satisfy those constraints without creating leaks or contamination. Cities that have piloted predictive mapping and keyhole techniques report meaningful reductions in surface restoration and crew time. Scaling those pilots requires sustained investment in data infrastructure and changes to procurement rules that currently favor lowest bid single-site contracts. The prize is not cheaper pipe, but a process whose cost per connection moves closer to the material floor once the coordination overhead is engineered out. Older neighborhoods contain undocumented modifications that no model can anticipate. The practical answer is to treat the model as a high-probability starting point that still allows a short confirmation step rather than a guarantee that eliminates all field verification. Trenchless methods cannot handle every configuration of bends or obstructions. The redesign would therefore sequence jobs so that the remaining open trench cases become the exception rather than the rule, preserving the bulk of the savings while the exceptions are handled with standardized equipment. Each of these moves attacks a different layer of the idiot index: data uncertainty, mobilization waste, and fragmented purchasing, rather than attempting to reduce the already low cost of the tubing itself. When the material cost of a connection is already trivial, every added dollar traces back to a separate handoff between records, permits, crews, and inspectors. Treating each replacement as an isolated construction project locks in that overhead. Treating the entire inventory as a single logistics operation opens the possibility of shared data layers and repeatable crew patterns. The same logic applies to any distributed infrastructure task whose price is dominated by site-by-site coordination rather than by the atoms being moved. Tomorrow we will examine another domain where the raw material floor and the finished cost sit far apart. Which city or utility will first publish the actual per-connection cost breakdown that would let others copy the lowest overhead sequence? That's a wrap on today's First Principles breakdown. The ideas travel further when you pass them on. Send this to a fellow builder. I'm Patrick in Vancouver. See you tomorrow, and if you'd rather watch than listen, find us on YouTube at Nerra Network. Links in the show notes. This episode used AI voice synthesis of my voice. Editorial selection and analysis are my own.